So now we're going to use our newfound properties of product property and quotient property to solve equations. So you can see here that you have an equation because it has an equal sign, and it has two separate logarithms, but they have the same base. See that? So we're going to use this quotient property right here, because it was a subtraction, to mush them together and make one logarithm out of it. See, the only way to solve logarithmic equations, here, let me talk while I'm typing this. The only way to solve an equation that involves a logarithm that you know of at this point is to rewrite it. But the thing is, you're rewriting using the definition. And if you look at the definition, which I'll bring right up, it's right here. Exponential logarithmic forms property. That's the definition, right? So if you look at that, it only has one logarithm, right? So you need a single logarithm, but you have two logarithms in this problem. So we need to make this go away and make it so there's one logarithm. So what we're going to do is we're going to mush them together. And we're going to make it so it's 12x over 6 equals 2. Remember that the positive ones go on the top, the negative ones go in the denominator. Now I have one logarithm, I know, but I'm going to actually simplify this just a little bit first, because we all know that that's 2x, right? Because 6 goes into 12 two times. All right, so now I'm going to use the property. So let me put it this way. I use the quotient property right here. And then the next step, I just simplified a little bit, right? Try to make it a little bit cleaner inside there. All right, now I'm going to rewrite using the definition. So 7 to the 2 is equal to 2x. So this is in exponential form, right? And that means 49 is equal to 2x, and everybody knows how to solve that, right? Hopefully. Actually, I'm going to flip it around. 2x is equal to 49, so that means x is equal to 49 over 2. Right, because you divide both sides by 2, and everything would be great. All right, so there we go. X is 49 over 2. If you want a decimal for that, that's, I don't know, 24.5. So if you like that better, that's fine. All right, so that seems pretty simple, pretty straightforward. Let's see what the next one holds for us, because I think it's going to be harder. That tends to be how these go. Oh yes, okay, so we got a little bit more of a mess going on this one. So let's see here. So we have 2 log base 3 of x squared, let's see, plus 3 log base b, or 3 of 2x is equal to 4. Okay, so the first thing we're going to do is we want to use the power property to move those logarithm coefficients up. So we'll make it x squared squared plus the log base 3 of 2x, oops, sorry about that, log base 3 of, come here, having issues, there we go, 2x to the 3 equals 4. Okay. So that means the log base 3 of, now this is x to the 4th, plus the log base 3 of 8x to the 3rd, because it's really 2 to the 3rd, x to the 3rd. All right, so what I did here was, to do this step, I used the power property. And then to do this step, I'm just doing some simplification. Okay. Now I'm going to use the product property, where I'm going to put them together. So it's the log base 3 of x to the 4th times 8x to the 3rd. Oops. X to the 4th. There we go. Times 8x to the 3rd. There we go. Equals 4. So I'm using the product property, sorry. Product, if I could spell, property, to push those together and make one logarithm out of it. Okay, so this is the log base 3 of 8x to the 7 equals 4. We're just doing a little simplifying right there. All right, now we're going to rewrite, because you need to solve this for x. x. The only way to get x out of here, this logarithm, the only way to get it out of the logarithm is to rewrite it. So I'm going to rewrite it. 8x to the 7th equals 3 to the 4. So it's 3 to the 4 equals 8x to the 7th. And 3 to the 4, by the way, is 81. So I'll write it that way. So 8x to the 7 is equal to 81. As a matter of fact, you probably would have been happier here. 3 to the 4 equals 8x to the 7, like that. Okay? And then I just flipped them around because I like the x's on the left, that's all. All right, I'm going to divide both sides by 8 because we don't want 8 in there. So that leaves us x to the 7. Oopsie, not there. Sorry about that. X to the 7 over here because on the left they're going to go away, right? Oopsie. Just having all sorts of issues. There we go. So 8 over 8 makes 1, so that's gone. Equals, and then 81 over 8, whatever the heck that is. Let me grab a calculator. 81 divided by 8 is 10.125. Okay. You still don't have x by itself, but you're close. But you see how x is raised to a power. We don't like that. So what we're going to do is we're going to raise it to its inverse, which is 1 over 7. And of course, if we do it to the left-hand side, we have to do it to the right-hand side. Now you might be thinking, oh, take the log of both sides. No, 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 no. You only take the log of both sides if it's a variable in the exponent itself. If it was 7 to the x, then you take the log of both sides. When it's x to the 7, that's something we learned in chapter 4. You just take 1 over 7 to both sides. So you have x is equal to whatever this is to the 1/7. So let me find that. I'm going to take 10.125, I'm going to raise it to the, and again, if you have the old system, you have to use parentheses, 1 over 7. If you have the new system like I have, you don't have to bother because it has a little superscript there. So it's 1.39. Oops. Let me do squiggly equals because we're rounding here. 1.392 it was. And that's it. We are all done with that section. So I hope you enjoyed. There is actually a little bit more to it that we are not covering, which is called the change of base formula. So if you want to read up on it on your own, that's just fine, but we're not covering it in class. And nor am I requiring anybody to know how to do it. So you can ignore it. All right, I will see you back here for 5-6, which is natural logarithms. So I'll see you then.